Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this final video on unsupervised learning methods, we are going to talk about neural network models. And this includes restricted Boltzmann machines, Bernoulli restricted Boltzmann machines, and stochastic maximum likelihood learning. So these are all related to Boltzmann machines, and this is not a mathematical in-depth video. This is a simple overview of what these methods are and how we can use them using Scikit-learn. So what is a Boltzmann machine? If you are familiar with the neural networks, we have seen a perceptron earlier, which is a single layer neural network. In case of Boltzmann machine, imagine that we have all these nodes, and the ones in green are the input nodes and the ones in gray are the inner layers. So that's the inner layer, so we can call it the hidden nodes. In this case, all the nodes are connected to each other, so even the nodes that are input nodes are connected to each other, and the nodes in the hidden layer are also connected with each other, along with the input connected to the hidden nodes. So that's a Boltzmann machine. And what scikit-learn has implementation for is a restricted Boltzmann machine, which in this case looks like this. We have these two layers. We have the input layer, we have the output layer, and so not the output but the hidden layer. And the input layer, now in this case the nodes are not connected. Similarly, in the hidden layer the nodes are not connected. The only connections are exist are between the visible layer, which is the input layer, and the hidden layer. So V1 is connected to all the edges and vice versa. So in this particular video, we are going to denote this each node in the visible layer by Vi, and the weights associated with each of these connections by on the symbol W, and each node in the hidden layer is denoted by Hj. So H1 is the first node in hidden layer and V1 is the first node in the visible layer. Now the, the restricted Boltzmann machine is given by this energy function uh, E, E of V comma H, where V and H are the binary vectors. So this is the input vector for the visible layer and this is the hidden layer, and it is given by this relation on the left hand side, where this W again is the weight matrix. Vi is for the visible node, Hj is for the hidden node, and then we have these bias terms, bias weights added to each of the layers. So we have the bias term Bi added to the visible layer, and we have the Cj added, term bias term Cc added to the hidden layer. Now, based on this, we can calculate the joint probability by this relation right here. Is P of V comma H is equal to e to the power this energy function divided by z, which is a normalizing constant given by this relation right here. And in case of Bernoulli restricted Boltzmann machine, the inputs have to be, according to the docs, it has to be either binary, that is 0 or 1, or it has to be a value between 0 and 1. So probably we can threshold it to convert it to either 0 and 1. So maybe if let's say if 0.5 is the threshold, then anything above 0.5 could be 1, below 0.5 could be 0. And following from the previous equation, we can uh, calculate the conditional probability using the Gibbs sampling method. We are not going into detail of how Gibbs sampling works, but here is the relation. Basically, we have the input vector V. We use that to predict H. So probability of H given V, and that is calculated by this sigmoid function, where sigma of x is given by this 1 divided by 1 plus e to the power minus x. So this x here, right here, would be this value that's in the bracket. So sum summation of over I, wij, vi plus cj, and that will give the predicted value for the hidden nodes. And once we have that, then we can come down to this relation. The given the value of hidden nodes, can we find the value for vi? And once we have those values, we can then compare the existing values of the nodes in vi with these new values, and if they are farther apart, we can uh, apply correction. And the idea then is to get as close as possible to the original values in the node, uh, uh, as these new VIs are predicted. And in doing so, uh, again, before we get into this, the Bernoulli RBM that's in Scikit-learn is also known as stochastic maximum likelihood or persistent contrastive divergence. Uh, these are mathematically intense topics. We won't be going into the depth of these, but I'll give you a brief walkthrough on what these indicate. So here we have the equation for log likelihood. So log of P of V is equal to log of this term and then this term right here, where we are going to denote this term by phi, and this is phi plus and phi minus. Now what happens is when we try to find the derivative for finding the derivative of the positive term, we can do that, so that is doable, but it is not possible to find the derivative of this negative log term, and it is intractable, and therefore an alternative method to go around that issue is using a contrastive divergence algorithm. And together, all this is saying is that uh, we can use this type of setup to generate new values of vi using the restricted Boltzmann machine. So it is a type of a generative model, and the use of that model is to it can be used for feature extraction. So let's say we have these values for x train. So we have 1 and 2 features, and we have y train, we have a x test. So what Bernoulli RBM can do is uh, it can give us the features. Here we just have 2, so it doesn't make sense, but imagine if we have more number of columns for x train, then the output of Bernoulli RBM can then be used as an input to a classifier. So here in the pipeline, we have RBM, which does the first pass on extracting the features, and then those values are then passed on to the logistic regression in the second part. And after that, we can use this pipeline to fit and predict the values as shown here. So that was it for this video. This was a very brief overview. If you still have any questions, comments or suggestions, please let me in the comment section below. I hope to see you all in the next video. This concludes the part of unsupervised learning methods that are available in Scikit-learn. I'd really like to know what your thoughts are on how the videos were, how informative they were, or how they could be improved. And I hope to see you all in the next section in Scikit-learn. Until then, please like, share, and subscribe. Thank you.